My name's Adam Bartsch. I'm the director of the Head, Neck, and Spine Research Laboratory at Cleveland Clinic in Cleveland, Ohio. And we study all modes of head, neck, and spine injury. And in particular, I'm most interested in studying the effects of head impacts and a potential for concussion or subconcussive impact accumulation. And this could be in athletes, and it could also potentially be in soldiers. So one of the interesting things about concussion in athletes is that the numbers are really all over the board, and it's actually difficult to quantify the problem. So if you look at one publication, it says anywhere between 1.6 and 3.8 million concussions occur to the nation's youth every year. And then you look at some other data and it says maybe it's more like 173,000 concussions yearly. So it's widely acknowledged that it's a significant problem. I think that those statistics alone, the fact that you have at least an order of magnitude difference between reported injuries, means that we still don't know much about it in spite of the fact that awareness is growing. One of the big issues right now is it's very difficult to know, in particular for children, it's very difficult to know how hard and how often they hit each other because there isn't a tool available to quantify it. And some of our preliminary studies, one of which was funded by the National Football League charities, we went out and we tried to study 7, 8, 9, 10-year-olds and look at their helmets and look at their running speed and their neck strength. And the summation of all of that work was that we really needed a tool to use on the field of play to measure them as they run into each other. So one of the projects that we're really excited about is what we call the Intelligent Mouthguard. And essentially it's a mouthguard, a standard mouthguard that you would get if you went to your dentist or you ordered one of our mail-order kits, except it has tiny MEMS or micro electrical mechanical sensors inside with a little computer and a little flash memory module. And this is nothing new. This idea has been around for over 60 years. It's just now the technology is to the point where we can fit almost everything inside the mouth that we need. The idea is that we want to be able to collect impact, intensity, frequency, and duration for folks participating in athletics. And we want to be able to compare those impact doses with clinical measures such as your cognitive ability or your vestibular, your balance, or the ability of your eyes to track motion in the field. And the hope is that we'd be able to actually quantify what level of impact corresponds to what level of decline in brain health. We're collecting trillions of data points, and we'll be collecting trillions and trillions and trillions of data points as we go forward. And there's going to be all sorts of mathematical modeling operations we're going to have to do to cut all that data down to size to make sense of just piles and piles and piles of head impacts. But we feel like we have to start with trying to quantify the problem. So quantify the engineering aspects of the problem in head impacts, and then quantify the clinical aspects of the problem through a concussion application that's being developed by Jay Alberts at the Cleveland Clinic. The sensors themselves are about the size of a Tic Tac, and then the circuit board is about the size of half a stick of gum. If you think about maybe a piece of juicy fruit or something, you cut it in half long ways, that's about how big it is. And you could actually take it and you could wrap it around your finger if you wanted to. Currently on board the mouthguard, we have a flexible printed circuit board to which we mount a 3-axis MEMS gyroscope, and then we have single-axis MEMS accelerometers that are controlled by a microcomputer, a flash memory module, and a rechargeable lithium polymer battery. So we can collect approximately 4 hours of data on one charge of the battery. We can collect up to 250 impacts per session before we download the data. Impacts can be up to 500 G-forces. So to give you an idea, the most severe hit ever recorded in the NFL was about 200 Gs, give or take. And we sample at 4 kilohertz, or 4,000 times per second. We're taking a sample of the data that's on board. So if you had Ray Lewis hitting the Cleveland Browns quarterback off a dead sprint, that hit is going to be in the neighborhood of 100 G-forces or so. And certainly impacts are quantified on linear motion, which is the G-force number, but also rotational motion, which is angular acceleration or angular velocity. And certainly your brain tissue, you could go into a lot of math about why both of those parameters are important, but people are looking at both quantities. But the top 1% of hits are in the range of maybe 80 to 100 G and above. The really, really common hits, especially in high school or college, are in the range of maybe 30 G or so. If you were to wear a mouth guard and walk down the stairs or plop yourself into a chair, you're talking about an event that's maybe 5 Gs or 7 Gs, thereabouts. So it gives you an idea of how hard people are getting hit in the head. So the big question right now in my mind is which is worse? Is it the KO, the knockout hit, or is it an accumulation of hits that result in somebody like, for instance, Mike Webster, who was the center for the Pittsburgh Steelers, who died at 50 from homeless, penniless, and died of dementia. He had never been diagnosed with a concussion. So certainly there's a question about what we call in the, I guess, medical lingo, acute concussion, which is diagnosed within 72 hours, or non-diagnosed subconcussive injuries that could number in the thousands by the time somebody would be finished playing a sport. We have absolutely no idea where the line in the sand is for how many impacts are too many, which impact is too hard, and how many impacts over many, many seasons you could absorb and still be okay. Once we can actually go into the laboratory and we can whack crash test dummies together with the same force that they're seeing on the field, then we can start figuring out which helmets or pads or air bladders would reduce those impact forces the best. If we don't have that data from the field, then all we're doing really is making an educated guess about what sort of helmets might be the best.